This is my partner, Daniel Mandeli. We're working on the FM Approvals project, automated light intensity measurement for visual notification appliances. FM Approvals is a company that certifies products with a focus on property loss prevention. One such product are visual notification appliances, also known as fire alarm strobes. One's pictured here. These are measured for their light intensity output in the alpha and beta axes. And see what that means on the next slide. Here we have their basic setup for testing. We have the fixture on the right side and the sensor on the left. The fixture has a rotational alpha and beta axis that keep the strobe at a fixed distance from the light meter. When we started this project, FM Approvals, almost their entire setup was completely manual, and a full test takes, it's several hundred measurements, and setting those manually takes a very long time. Our best anticipated outcome would be to create a fully automated system that is capable of recording and compiling all of the light intensity measurements for all the angular combinations. Pictured here is we have their old fixture when we started this project. You can see that there's one wire here, but this one's all manual, and there's a lot of weight being put on it. So our first major accomplishment was to redesign this fixture so that we could automate both motors, then automate the light sensor, the stepper motors, and finally tie it together with a graphical user interface. The first major challenge we overcame was to redesign the fixture with automation in mind. This mechanical task is outside of the traditional electrical curriculum, but by testing, researching, and verification, we were able to build this design. This uses the same Thorlabs model for both motors and works with many of the parts FM Approvals already had for this purpose. It also puts minimum weight on each sensor, on each motor, which allows us to use the same ones. What's not pictured here is that 3 linear translators, which only exist and they're set once per test because each strobe is shaped a little bit differently. Our next major challenge was automating the light intensity meter. This light intensity meter does have the capability to log data over USB, but it lacks any built-in automation capabilities. What we did is we integrated it with a Arduino Uno microcontroller. To do that, we had to build a custom connector first, then establish a handshaking protocol so that we could send commands from the PC to the microcontroller. Finally, those commands would then trigger the specific functions of the light meter and allow us to automate it. With a fully automated light sensor, we're now working on accurately counting and detecting the light flashes from the strobe.
Thank you, Elliot. So with the design of the fixture set and ready, our next key step and challenge was to figure out a way to actually move both stepper motors simultaneously. And we wanted to do this strictly via software. So we conducted some research, and we found an open source Python module which actually wraps itself around existing Thorlabs libraries. And so this would use the Thorlabs proprietary communications protocol in order to send signals effectively to the stepper motor controller and drive both motors. And this is done all via the Python programming language. So now that we had a set method of driving both motors accurately, our next step was to actually automate the process of moving both stepper motors to follow a specific set of standards. So to start with this, we first defined the standards within a Python library in which these standards would be imported at the beginning of each test, and this would be prompted by user input as well. So we're still working on the algorithm to actually implement some of the light detection within this program, but we're very close. But as of now, we are able to go through each angular set of rotations. So looking here at this demo, we could see the beta axis on top and the alpha axis on bottom, where the beta axis will go through its full set of rotations, while the alpha axis stays in place. The beta axis and alpha axis both have a specific range at which they operate, as well as various increments depending on the standards being tested. So looking strictly from a software perspective, as well as keeping the scope of the project with the best anticipated outcome in mind, this is our design. So now that we have both systems working individually for our best anticipated outcome, we'd like to combine these two systems into one autonomous system, in which the host PC will send signals to the motor controller to drive both motors, set the angles, which will send a signal back saying that they're set, which will then send signals to the microcontroller, which will trigger functions within the light intensity meter, collect the data, send that back to the host PC, which will collect all the data and output it correctly into an output file. So one of our biggest remaining challenges is to actually develop a graphical user interface to wrap this entire system up. So this interface will allow the user to both initiate a test as well as track the progress of the test as it's being conducted. So we have two key features in mind for this interface. The first, allowing the user to first customize any existing standards that we have already defined within our Python library, as well as add any future standards that may arise. We also allow the user to specify a specific type of file to output to in a table format. In conclusion, we'd like to thank everybody who has supported us this semester, and we'll continue to work hard next semester.